Human beings have been playing musical instruments for thousands of years. What I'm going to try to do in this video is to give a little bit of an overview of what you need to know about music. Turns out not to be very much, in order to test hi-fi amplifiers. And testing of hi-fi amplifiers falls into two parts. One part, which I'm going to emphasize, is technical testing. That is, using electronic and other methods to actually look at the signals produced by musical instruments. But there's a whole other part of this that has to do with listening. That is, being able to hear how a particular amplifier or speaker, or in the case of recordings, even the microphones and the acoustics of the recording hall and so on, have affected the music. In order to do that, it is necessary to talk about a couple of terms that in the music industry have one set of definitions, and in the engineering or electronics industry they have another. For example, the attack time, that is, the time that it takes for a signal to rise, and this is a very sharp, quick signal, but the time it takes to rise to its maximum value from some rest value in electronics is called rise time. In music, or at least in music theory, that is normally called attack. Both use frequency, that is the number of cycles per second. But generally in music, they refer to that as the tone. The particular qualities, that is the overtones, the harmonics that are produced by a particular signal, and to do that you'd have to look at this on a spectrum analyzer, we usually call harmonics or harmonic distortion or whatever in electronics. But in music, they generally refer to that as the color, or sometimes they refer to it as the timbre, T-I-M-B-R-E. So what you see on the screen is my attempt to illustrate how a particular musical instrument produces tones. And one thing that I would like to emphasize, because it's rather important when you're testing amplifiers, is if you simply test with a sine wave, that is a single frequency, or even a couple of frequencies, you're completely missing the attack or rise time characteristics of the amplifier. Second, if you test with a single or a couple of sine waves, you are completely missing the intermodulation that occurs when you have more than one sine wave. So what I'm going to try to do is to show how you can test some of those things electronically. But more important, you're going to discover that in the final analysis, it's how an amplifier sounds that really matters. After all, the purpose of the amplifier is simply to make the sound loud enough for people to hear it in a large room. And if you're reproducing a hi-fi sound, you would like that sound to be as close to the original characteristics in the hall in which that music was recorded, whether that's a large concert hall like Carnegie or a small recording studio. So let's get on with it, and the first thing I'm going to do is show you a little bit about a guitar's sound. The setup consists of that small speaker that you see there being used as a microphone and connected to that signal tracer behind, which is simply being used as an audio amplifier. Notice how at first the sound is quite loud, then it seems to die out, or at least die down, and then there seems to be a bit of time where it continues at the same frequency. That is called sustain. So let's take a look at that on the oscilloscope. Here you see the attack, and notice that, let me spread this out a little bit, the string does not immediately begin to produce a large excursion. The reason is this early cycle is just the string in open air. As it begins to resonate in the box of the guitar, those resonances increase the amplitude. And so what you're seeing here, that is this characteristic, is much more a result of the way that the guitar is built rather than the particular string that you pluck. However, this will vary depending on the particular note that you play. And it's this attack characteristic that you would like to have reproduced as well as you can in an amplifier. It's also the area that I think is most ignored by people in hi-fi. Now, by that I don't mean professionals. They pay a lot of attention to this. But a lot of people, when listening to music, don't hear this. Now, I'll admit, I'm not exactly a Mozart when it comes to my musical ear. But if you're aware of how this changes at the beginning, and then what happens to it, you notice that it then dies off a little bit, and then it actually comes back for a little while. Then the tone starts to level out. And this is what is called sustain. So there's an attack during which the instrument's output expands. Now, I used my finger to produce this particular string display. Let me now use a different system. Now I'm going to use the steel tip of this probe to pluck the string. Same string. I'm using a steel probe. Usually people use plastic picks, which have a slightly different quality, but I'm going to use the steel probe, partly because it is stiffer and tends to accentuate the difference between using your finger and using a pick. So now let's take a look at what the waveform looks like. It's rather different. Notice that at the beginning there is a kind of pre-strike. The rise time, that is the attack, is much faster once the string gets vibrating. This is actually the sound of the pick scraping on the string. And then when the string is actually plucked, you get a very fast attack, a fall off. Remember, the attack is a characteristic mostly of the instrument, but if you use a pick, you get a much faster attack and then a fall off. Then you see it goes through the same characteristic, that is, there is interference in the sound box, reduces the volume, and then the volume builds again, falls, and then reaches a more or less sustained level until the energy in the string is dissipated. You might say, well, this is all very interesting, but what does it have to do with testing amplifiers? Well, this characteristic of a pick itself is not the interesting thing in terms of amplifiers. What is interesting, though, is the much faster attack of this sound. In other words, I said earlier that the attack is due to the sound box, and it is, but it's also due to how clearly or how sharply the string is struck. The second thing is, if you test with sine waves in an amplifier, you will be testing this part. But frankly, most people find that the most interesting part of music occurs right in here. It's the difference between, say, Jimi Hendrix and Segovia. It's the difference between a violin and a guitar. Violins tend to produce a lot of overtones, but so do guitars. That is, a lot of harmonics. But a struck string has a quite different attack characteristic from a bowed string, as on a violin. Similarly, a piano has a different attack characteristic from a guitar. You can hear all these differences. That is, you can pick out the guitars and the pianos and the violins from instruments like woodwinds and flutes and things that tend to produce a much clearer tone. That is, fewer harmonics, much softer rise or attack time. And so what I'm now going to talk about is how you can use square wave analysis to measure the ability of the amplifier to respond quickly to the attack of the music and to sustain the level over a long period of time. One of the kinds of waveforms that you really need to use for the testing of amplifiers for music is some kind of a burst signal. Now that's what this is. This is a burst sine wave. The signal comes on, it's a sine wave for a period of time, and then the signal goes off. What we're trying to do here is simulate instruments like plucked guitars and things of that sort. Now the particular generator that I'm using is the Siglant that you see over there that I previously compared with another generator that is still on the market, the Rigol over there, the 1022. What I would like to do now, though, is turn to a little bit of the testing, the methodology, and the equipment that you might use, and then hopefully conclude with a little bit of a demonstration. We've talked about a little bit instrument types, and I showed you an example of a plucked string instrument. That is the fact that it generally has a fast attack compared to many other instruments used in orchestras and bands. The example I used was the guitar. Generally, you can emulate the fast attack characteristics of a plucked string instrument with a tone burst like I just showed you. A bowed string instrument like a violin often has a lot of overtones. So for that, you want something that is rich in harmonics. And in a minute, we'll talk about some signals that you can use. Actually, you only need about 3 or 4 different signals to test electronically the range of these instruments to the extent that you can do all this electronically. But as you'll see, you eventually get to a point where electronic testing is just not giving you any more return, and you have to actually go to a hearing test. The human brain, the human ear, is actually the best test instrument for music. So percussion instruments, especially instruments like cymbals, in addition to high volume, which of course tests the linearity of your power amplifier, they also are rich in harmonics, very much like a violin. And of course, the difference is that the excursions on a percussion instrument generally go from 0 to very high volume and then fading back to 0 again. Wind instruments have a particular characteristic that is peculiar. It's an asymmetrical waveform. And the reason for that is, if you think about an instrument like a trumpet, the air has no trouble coming out of the end of the trumpet. But while it's being blown, the air has a lot of trouble going back in. As a result, the compression of the waveform is much more pronounced than what is called the rarefication. And as a result, wind instruments tend to produce asymmetrical waveforms. Now, I'll talk about that one in a little bit. Obviously, in the final analysis, you're dealing with mixed instruments. So you have to deal with music that changes dynamically. And frankly, while you can do some testing electronically on that, as you'll see, for various reasons, you may choose to minimize your electronic testing and go straight to a listening test. You have to consider the type of music you're going to be playing on the system, because a system, for example, that is appropriate for classical music might sound too soft or not harsh enough for someone who prefers, say, heavy metal. The load is also important. Remember that most tests electronically are done with a resistive load. Well, if you watch some of my earlier testing hi-fi amp videos, you know that speaker impedance is variable. And so the load varies with the speaker, whereas with a resistor it does not. Finally, you have to consider the room acoustics. It really does make a difference when you test an amplifier with a resistive load. You're not considering either the speaker characteristics or the room acoustics. So let's talk a little more about electronic testing, maybe do a little demo, but I would like to get on to the idea of using your ear to test for music fidelity. So far, I've concentrated on electronic test methods, and some of the earlier videos I did on testing hi-fi amps using the analog discovery and the Syncor power analyzer and so on are focused purely on electronic. In this case, you can measure things like the power output, the frequency response, that is, for example, the gain and phase, and if you noticed, we did some of these using a network analyzer that's built into the analog discovery in some earlier videos. Transient response. Now, normally, people use square waves to test transient response, and that's perfectly appropriate. You should do that. What I'm advocating here is that you also add a tone burst, and I'm going to try to show you an example of how you would test using a tone burst later. The test equipment that you might consider owning for this include a watt meter, some kind of dummy load, an oscilloscope, and in some of my previous videos I used not only a conventional oscilloscope but also a USB oscilloscope like the analog discovery. A signal generator, generally one with an arbitrary waveform generator output. And I've shown you here the signalant generator that I normally use, as well as a Rigol that is the one that I used to use. You can also use something like the analog discovery, which produces that. A network analyzer, and here's where the analog discovery becomes a good test instrument. It does contain a network analyzer. Finally, or in addition, a THD, that's Total Harmonic Distortion Analyzer, and I showed a couple of videos on that kind of analysis, and one of the instruments that I used was a Keithley 2015 THD meter. Spectrum analyzer can be useful. One of the problems with most spectrum analyzers today is they are designed for RF work, and while some of them go as low as 9 or 10 kilohertz, what you really need is something that will go down to around 20 hertz or 40 hertz at the low end. For that reason, you might want to consider using an FFT function in an oscilloscope rather than buying a separate spectrum analyzer. Finally, intermodulation analyzers. They're not used as much today as they once were. They came into vogue, and I may show you one of these. I have an old Heathkit intermod analyzer. These sort of fell out of favor, and one of the reasons is, frankly, they'll show you if you have really bad intermodulation distortion, but frankly, you can find that faster, in my opinion, by simply listening to the amplifier. So let's talk about listening before we move on to the conclusion of this and do a little bit more electronic testing. A good test record, CD, tape, however you source your music, can be your best friend in analyzing a particular amplifier. Now, you really should do your listening with the intended speakers. If you try to do your testing with one set of speakers and then you hook up a different set for listening, you'll find that the amplifier doesn't sound the same. Some of the things you want to listen for are warbling. Warbling is where in the original signal there, for example, is a mixture of low frequencies with mid-range. And what often happens is the low frequency tends to modulate the mid-range. What I mean by that is the mid-range rides on the low frequency. It shouldn't. The low frequency should come through, the mid-range should come through. What you should hear should be a mix of the two, but it should be a linear mix, not a modulation. So if you listen to a mid-range, for example, an orchestra, and then a low frequency comes in, let's say an oboe or something of that sort, and all of a sudden the mid-range starts warbling, that is, varying in volume. What you've got is some intermodulation and some nonlinearity in the amplifier. A good thing for this is if you have some music that contains violins by themselves and then those same violins with an oboe or some other low-frequency instrument. That's some of the best music to test for this warbling. Intermodulation. Piano chords are the best way to, at least for me, to do this. And understand, I'm not an expert in this. I used to do this a fair amount, but that was 30 years ago. Particularly if you can find a situation where, for example, the same notes are being played in the melody, and then the chord comes in, you can often hear it sounds muddled when the chord is played. That's because there's intermodulation. And frankly, listening to a piano concerto, for example, will tell you more about intermod in your amplifier than a lot of the old intermod analyzers, and that's one reason they fell out of favor. The other kind of nonlinearity that often happens in amplifiers is where you have a loud excursion accompanied by mid-range. So, for example, I use here the 1812 Overture. There are passages in the 1812 Overture where the mid-range is of medium volume, and then there are loud percussion sounds. Listen to those, and I think what you will see is if you have a nonlinear amplifier, that is an amplifier that generates intermod or harmonic distortion at higher levels, what happens is even though you listen to the mid-range at low volume, when the percussion comes in, it drives your amplifier into that nonlinear range. Now you can test this to some extent electronically. So enough about this. One thing that I will say is no matter how much electronic testing you do, you will never be able to replace the human ear, at least perhaps I'm being too dogmatic. At the present time, I don't think that there is a single set of electronic tests that can replace the human ear and the human brain. Now let's demonstrate how we use a tone burst. This is a circuit that I've put together purely for the purposes of demonstrating how you use a tone burst. In this case, it's a simple, approximately gain of 20 integrated circuit or operational amplifier. 22K feedback, about a 1K input resistor and a 1K balancing resistor to ground. I've now applied the tone burst to this circuit. It's built over there on a little breadboard. And let's take a look at what it looks like on the oscilloscope. What you see on the oscilloscope is the input tone burst here in yellow and the output tone burst in blue. Now I have deliberately offset the amplifier to create clipping on the negative edge. What you will find with some amplifiers is not just that you get some distortion on the input as this shows, but also when the tone ends, you can sometimes get ringing in the output. I suggest adding tone burst to the tests you do, the electronic tests that you do on amplifiers, music amplifiers. But that doesn't replace the use of sine waves, including frequency analysis, Bode plots, and those sorts of things, as well as square waves to look at transient response. So what you see here is an example of the kind of distortion that you might miss in a regular sine wave analysis, but in a tone burst you might be able to see it. In the final analysis, you really need to listen to the amplifier under the conditions, or as close as you can get to the conditions that you're going to be using it, with some music that have the characteristics that I've talked about. And so part of the purpose here is to talk about musical instruments so that hopefully you'll be able to know what to listen for, as well as how to choose your test music if you go into an audio store to buy a new amp or some new speakers. I haven't been making as many videos lately as I would like. I hope that will change, but for the time being, I wish you have a nice day and hope to see you in a future video.